yeah, as Ma already said, in this talk, we're going to talk about how to actually implement the ideas from the previous talk to actually get better auto-formalization results. And there's going to be some overlap with the previous talk, but maybe that'll help, like, with the understanding and give you another perspective.
Okay.
Because I wasn't sure if everyone was going to be there for the previous talk. Right. Yeah, mathematicians have gotten very interested in formalizing mathematical mean. There have been various projects about formalizing quite modern mathematics in mean, and now there's like this project of formalizing even Fermat's last theorem, which is like at the almost cutting edge of number theory. And why are we interested in formal mathematics? Well, formal mathematics has the advantage of being very precise and checkable, has a lot of semantic information. The disadvantage is we have a lot more informal math written than what has been formalized. So obviously you want to actually automatically formalize all this info. Right. So what does auto-formalization look like? So you have an example statement and the formalization mean. So the statement is about group theory. If X is an element of infinite order in a group G, prove that the elements X to the n are all distinct. And in mean, you would write it as on the right-hand side. So you would introduce a theorem with the name formal, and you would introduce the type G that happens to be a group, and X, an element of type G that satisfies the hypothesis that for all n, X to the n is not 1. And then the conclusion is that for all m and n different integers, X to the m is not X to the n. And already in this example, we can see a few challenges of auto-formalization. First of all, non-trivial syntax. So the type star thing is actually not something that's directly in Lean, but a separate concept that's defined in Mathlib to make it easier to work with universe levels. There's lots of implicit types in the natural text. So the n is not defined to be a natural number or integer, and that has to be inferred. Also, we don't say that G is a group. We just assume that from the notation because G is often used for groups, and this sounds like a group theoretic statement. There's informal shorthand. So infinite order, we don't actually say the order is literally infinity, but it's just a shorter way of saying the hypothesis with a quantifier. And also, the thing that, for example, language models struggle with is that there's still a lot of older on the internet. So sometimes they try to output Lean 3 instead of Lean 4, where, for example, the version 3 of Mathlib group would be lowercase. Doesn't be syntax error. And this continues to be a problem. It's slightly small. All right. So, as in the previous talk, I would like to advocate a probabilistic viewpoint for auto-formalization. I think probabilistic reasoning is key for disambiguation, as we saw in the previous talk. To infer like missing steps, assumptions, to fix errors, statements that may be helpful but not literally correct, and to also be able to fuse hard constraints, such as one things to be parsed correctly and being typed, like soft signals such as plausibility or like the back translation that I was talking about. And ultimately, we want these probabilities to kind of calibrate uncertainty and to tell us how confident we can be in formalization. And yeah, language models play into this because they give us a distribution over texts or code. And we want to tweak this distribution. For example, we might want to enforce that the language model generates Lean 4 instead of Lean 3. And since there's not a lot of data about such formalized texts, we want to kind of leverage computation and inference times when we generate the text. Okay, so let's look at how we could go about asking LLM to formalize the statement. we could have a prompt like this, where we just first say natural language statement is what I told you before. And then we say lean code translation, we start a lean code block, and then ask the LLM to continue at the end. And I'm also going to show you for each token that the LLM creates the probability color-coded. You might get something like this, which would be ideal. So this is the correct formalization, one correct formalization of the statement. And you can see each of the blocks is like one token that the LLM generates and assign the probability to. For example, you can see that after the word formalized, the LLM considered various things, like the first two options want to continue, the name of the theorem statement, the fourth option starts to write a comment, and one other option is to actually open a bracket. Also, at the point where the G is output, G is by far the most likely option because apparently the LLM thinks, quote unquote, that the group has to be defined first. So X might also be something that has to be defined, so that's the second option. At that point, when we say G is a type, apparently the language model is tempted, again, anthropomorphizing, which maybe I shouldn't, to say group. But in Lean, this would be wrong. We first have to say it's a type, and then say that this type implements the group type class. And the third option is actually what we would do in Lean 3. So we're coming back to that point, the lowercase group. Right. Here's an example of formalization where things have gone wrong. So here we started with a brace instead of parentheses. And apparently this changes probabilities in some weird way. So braces are used for implicit parameters in Lean, such that the LM thinks the group is more likely than type, and this would be unfortunate because this doesn't type check. Okay, so how can we, so in this talk I want to talk about how we can enforce constraints such as type checking on these elements. And as alluded to in the previous talk, we want to use Bayesian inference for this. And the idea is that to get the distribution of texts conditioned on certain constraints, well, how is this distribution defined? It's defined using Bayes rule, where we take the prior distribution over texts, which is given by the LLM, the language model, multiply them by some likelihood given by the probabilities we assign for the constraint to be satisfied for a given text, and then we have to divide this in normalizing constant. And what could those likelihoods be that we condition on? There's kind of two types. There's hard constraints, which can be 0 or 1, such as syntactic validity, well-typedness, provability, and then the soft constraints, which kind of continue a signal between 0 and 1, such as whether how plausible the statement is, the style is good or not. We could also try to leverage distances in embedding space, which is on the previous slide, those kind of things. And the hope is that then the posterior distribution will contain better formalizations. So these kinds of constraint we impose, we also call potentials, which is this likely function of constraints given a text. As I said, there's like binary potentials, which take a text and output 0 or 1. So this is something you can actually write code for. And you could, for example, invoke the Lean parser and say, is this code syntactically valid? Does it type check? Are there linter warnings? And can a counterexample be found? So this could be an application of plausible tactic in the previous talk. And for those continuous soft potentials, you could, for example, have another language model to store the output. You could also use cycle consistency, which I'll talk about later. And then we want to sample, again, by the prior distribution reweighted by these potentials. So this idea has actually been used before in different settings. So here the task is slightly different. We don't want to generate Lean, but instead want to generate code that executes a valid SQL query. And So the way this could look like is we have like two generations. We don't just consider one generation at a time, but like several of them. And if like one fails, such as for example saying select age 4 instead of from, which is valid equal context, then we can stop that generation and keep the other components. And how to do that systematically, I'll talk about in a second. And similarly for Lean, we could use syntactic correctness, type correctness, example. And if we go to formulating proofs, even checking validity of proof steps. And the way this could look like is, for example, language models like to introduce parentheses for function applications, which is invalid syntax. So we would kind of stop these generations and keep the valid ones.
So yeah, it can be that the informal statement itself is incorrect, but you will force it to convert to something.
I mean, it depends on your choice of what constraints you want to impose. If you want to impose the constraint that format statement should be provable, then yes.
Or type correct, or because
I mean, type correct is something you always want for formalization, I would say.
But it might be that the original informal statement is type incorrect. Okay. And you want to find these errors because that's one. If that is one of the goals of auto-formalization, that you can check things. Sorry, this is maybe a general question. Or
that is fair.
Or checking existing mathematics or papers, submissions.
Fair, although I would doubt that most of the errors in mathematics papers are type errors. I would assume that they're more subtle than that. But it's a valid concern. But I think for most formalization projects, type correctness is something that you want.
But there is something that you want to be kind of benevolent. How do you say? You try to find the formalization that makes the most sense, so to say. Whatever the input is.
Is that actually was syntactically incorrect?
Yes, sure.
Well, typed, some of them will be accepted just to extend sense, put together semantical pieces together to make sense.
Yeah, maybe this is some. Sorry.
No, all good. Thank you for the comment.
It's a good question, actually.
Yeah, feel free to ask questions. Right, so now I want to talk about how we can actually sample from this posterior distribution after having applied all the constraints. And for this, we use a technique called sequential Monte Carlo, which I'll only be able to talk about very superficially, but there's been whole books written on this, if you're interested. So if we have a prompt that we want to complete, so here I'll just show the last part of the prompt, then the first thing we do is we don't just generate one completion, but like several. And these are called particles in sequential Monte Carlo. And each particle has a weight, which is initially 1. So in this case, we have 2 particles that generated the open brace and 1 that generated the open parenthesis. And then we keep generating, and at each step we kind of check the potentials, whether they the constraints, whether they have anything to say about that. But in this case, all the potential functions will be 1 because so far everything is syntactically fine. Then we keep going with the generation. We have G, colon, then type. Also, so far everything is fine. And then we close the bracket. And then we could already detect some mistakes. Like, for example, the type checker will say that proof is not actually type, but type path is essentially common here. So the type checking constraint would say this is wrong, so this gets weight 0, and the top one stays at weight 1. And this would similarly happen not just for weight 0 and 1, but also for those soft constraints. So you could also get a weight 0.5 there. And what happens then? Well, it makes no sense to keep the 0 weight ones around because they would have 0 probability. So what we do is we sample from the remaining particles. Here there's only 1 particle, so this will just be duplicated. But we had a more complicated set of particles with certain weights. We would resample from the remaining particles according to their weight, and in this way maintain the diversity of particles. And then we would keep going with each one, maybe generate again an open bracket. And in the end, we just get a set of particles with certain weights, which we can take as weighted samples from the posterior distribution. So one thing we needed in this example is to do type checking before the whole theorem is complete. So this is actually very difficult to get right, and so far we just have a heuristic way to deal with it. So the first idea you might try is to run the parser and type checker on incomplete generations, but there you just usually get unexpected end of input, which is not very useful. So instead, one thing you might try is ignore errors, let's say, that occur at the end of the generation, because those are likely related to the incompleteness. But even this can be unreliable. So this is a complicated example where the error location is kind of earlier, even though the error is just due to incompleteness. So this doesn't work. So what we settled on is to check the validity after each parameter or hypothesis in the theorem. And the way we do this is if we have an incomplete theorem statement like this one, right, which is saying expected end of input, we just add a dummy conclusion. We say the conclusion is true, and the proof is bi-trivial, and this is syntactically valid, so we can run the type checker, and in that case it would accept it. So this is the project value. But that's probably better, and I'm interested to hear your ideas. Right, so maybe don't read all of the slide. The point that this is supposed to illustrate is that even if things are well typed, they might still not match the intent of the original statement. So here the informal statement kind of is this topological statement about various sets, and all of these options here are well typed, but only this one happens to exactly capture the informal intent. Another thing you can observe with this, still some variation in the formalization. So you could, for example, get theorem names, or express the square of a variable in two different ways, either as literally squared or as multiplication by itself. And many problems, the LLMs struggle to get like one detail right. So in this case, there's a statement about a metric space having more than 1 point, and expressing this in Lean is apparently difficult. The LLM, so the correct way to translate is to say X is non-trivial, metric space is non-trivial, but it also tries other things like non-empty, which doesn't work, and infinite for whatever reason. So what we want to do is want to assess the mathematical content, not just the form, the sense of like parsing and typing. So the well-typedness potential check, yeah, checks the shape of the Lean code, but we also want to check the content, whether it matches the informal meaning. And the idea here is to go in the other direction, or to be able to leverage the ability to go in the other direction. So going from formal to informal is easier for language models, much easier than going to formal. And this led us to the idea of cycle consistency. So if we have an informal and a formal statement, then if we go from informal to formal, back to informal, this should roughly be the identity. I think there was a similar idea in and this has actually been used in natural language translation for a long time, like since the 1950s. Has also been proposed as a technique for auto-formalization, and related ideas, just still back translation, have been implemented. But we want to incorporate this into as a potential into a sequential Monte Carlo inference. And our idea is the following. We start with a formal statement, and then we ask a language model to formalize it. So we give the prompt, formalize the statement, and then we get like a couple of candidates from the sequential Monte Carlo inference. And then we want to know which one of these matches the original intent best. And in this case, it would be the first two. And the third one is slightly wrong because it says greater than equal to 0 rather than greater 0. And what we can do then is ask a language model to informalize each of those candidates, but not sample from that distribution, but just ask it what's the probability of this informal statement being a completion to the prompt informalize each candidate, and take the logarithm of the probability of that and take that as a signal how well how good the formalization is. In this case, we see that the first two, which are correct, give us like minus 104, minus 105, and the last one is incorrect, it's the initial. Right. So, in this case, we measured the quality of this back translation by using the probability of the language model generating the original informal statement when prompted to informalize. But there's other things. First of all, there's a problem that this might capture other signals than the truth value, such as the style in which it's written or something. So there's other things we could do. We could consider making use of embeddings, as in the previous talk, and compute some kind of distance in the embedding space as a signal for how good the formalization is. Something similar has been done in this neuropaper. So this is kind of cheap. Embedding is fairly cheap to do, but it's also a bit imprecise. And kind of more expensive thing we could do, which is high quality, but yeah, takes more resources, is to ask the language model to rank very well. And we did a little note on this for this toy example. So on the left, there's the 3 lean formalizations. The first column is whether they are correct formalization, which was labeled manually. And then we have the 3 ways of kind of assessing the quality of the back translation. So first column is the distance metric in the embedding space. And there seems to be a bit of signal, like the distance, it's a bit closer in the first 2 than the wrong one, but the first one is closer to the wrong one than to the middle one. The next column is what you saw on the slide. I think the probability of generating the original informal text. And in the last column, we asked Clouds on Import to rate each back translated informalization. And this is the result. So the first 2 got a perfect score of 1, and the last one got 0.8. So this is kind of the best signal, probably, but also much more expensive. Okay, so in our project, which we call GenLean, we want to put all of these ingredients together. So we use a language model. In our case, DeepSeek R1 Digital Llama 7C. Has 70 billion parameters, which is small enough that you can still run it on like the GPU in the cloud and don't have to like go to big LLM providers. We have a prompt of a number of formal pairs, which I'll show you in the next slide. We apply various potentials, such as the cycle consistency potential and the multi-typing stack. And then we run sequential Monte Carlo and get particles out, which run the weighted relations. And yeah, to tell you a bit more about the prompt, so the way it works is just like it gives one natural language example and a formal translation, and this 4 times for different kinds of mathematics. And then the actual natural language statement is going to formalize, and its formal translation control it looks something like this, which we don't read in detail just to give you an impression.
You didn't do fine tuning.
No, we just took the models as they were. Okay, so then we wanted to evaluate this experimentally, and this is the experimental setup. So as a benchmark, we took the mini M2S benchmark, which is consisting of informal formal pairs like this one here, and the formalization problems are like high school level Olympiad problems, maybe undergrad problems as well. We take the 7dB large language model. We run sequential Monte Carlo with 10 particles for each combination of the potentials. And to evaluate whether the formalization matches the intent of the original, we have Claude Sonnet 4 label it to be correct or incorrect. And we kind of spot checked it, whether the formalization made sense, and kind of agreed with our manual labels in 97% of the cases. And as an evaluation metric, we kind of took the weighted average over all the particles produced by sequential Monte Carlo, where we gave a score of 0 if it was incorrect and 100% if it was correct. And the results look like this. So we just run the LLM without any constraints, we get a score of like 13%. If we include the lean validity constraint, so that has to be well typed, it rises slightly to 14%. We just impose the cycle consistency constraint, we get also a bit higher, like 13.7%. And if we can combine both, we get to like 16.7%. So I think groundbreaking, but useful improvements, I would say, which we hopefully can improve in the future. All right. This brings me to the end of the talk. Yeah, as I said, our idea is to use Bayesian inference for auto formalization. To do the inference, we use sequential Monte Carlo, which incorporates various potential functions to kind of tweak the distribution to something that we want, such as the lean validity potential, which parses and type checks the code, the cycle consistency potential, which uses the idea of back translation to try to assess the matching of the informal intent. And yeah, the experiments that I just showed you was an improvement on the mini after. Thanks for listening and good questions.
Questions? Yes, welcome.
So, is it fair to say that every one of these potentials gives you 1%? So you need 85 more.
I mean, it's a bit more than 1% each, but
well, those are combined, yes.
I see your point. I would say it's much easier to write potentials than training a huge LLM. So in that sense, it can already be useful. But yeah, I hope that we can kind of improve the this potential. For example, this one also doesn't include the plausibility check, for example, which could be helpful for the mini FQF. So I don't think it'll get us like all the way to 100%, but it's a fairly easy way to improve existing models without having to do like heavy training, fine tuning, and that kind of stuff. So I think it can be a useful boost for existing models.
Thanks both for these talks, very interesting and really presented. But just coming back to the question that I interrupted. So maybe this matching the intent on informal text is a key to seeing that you are not forcing a correct something correct for something that was initially incorrect, because then the match of the obtained correct lean statement would be too different from the original informal statement.
Right.
If the informal statement was incorrect.
Yes, yes. So it could be useful in that way. Also, another thing you could do if you didn't want to exclude type incorrect ones completely is that you could just assign a weight of 0.1 or something to type incorrect statements instead of just ruling them out completely with a weight of 0.
Your examples, at least the ones you showed us, seem to be the kind of sequence of assumptions seems to be relatively low levels of dependencies. And more interesting or later in MATLAB parts seem to have increased that dependency and twiddliness of that pretty radically. How stable do you think the results are under such area changes?
I'm not sure what kind of dependencies you're talking about. Are you talking about dependencies within one theorem statement, or like
within one theorem statement and kind of you first declare G to be a type, and then you say it's a group, and then it has a couple of parameters that have somewhere to have been declared before, and then it's in the type, it's in the arguments, and those kind of things.
Right. So you think that would be a problem for kind of incremental type checking? Or
I'm asking you. You have the experience. I certainly don't.
So currently we haven't run it on like super complex mathematics yet. So the kind of benchmarks we ran it on are like mini F2F, which is like high school level problems. Also the ProofNet benchmark, which also includes like undergraduate mathematics to some extent, but nothing like super complicated, which you are talking about. So I don't know.
No, yes.
So,
Well,
Do you want to add something?
yeah, I was just going to add to that. I mean, one idea that we looked at doing is adding more context to the prompt. So you can imagine that you're trying to formalize a statement, but in context, and so you could include some of the steps before, after, and some of the group. You could also include how you formalize an initial section of it so far, so formalize the next statement in context of what you've already said. And so, I mean, there's a number of ways of doing that, but just including it in the formalization prompt could potentially solve some of them.
It would be opening a context by putting it into the prompt.
Yeah, to the formalization request, which like clearly will help to some degree, even apart from constraints and the constraints, and still preserve some of the information.
This is regarding the incremental type checking part. So the solution that you gave, that just put true and the proof is bitrivial. So you said that it's probably not the best way to do it, but why do you think so? That it's not like the most natural.
I mean, adding this, I think is fine. Like,
yeah, I think like
I just think we could like try to make it more incremental, basically. So like the conclusion is just like one block where we don't do like any incremental type checking, and you could imagine, for example, if there's an exists quantifier in there, that we start parsing the exists and then complete that with true as well, for example. But there could be more complicated things we could try to make it more incremental. That's what I was thinking.
okay.
gives no questions. Why have you chosen Monte Carlo?
Because okay, so the distributions that language models generate are like super high-dimensional, huge, right? So at every step of the generation, like there's like 50,000 tokens or so that could be generated. Then you have like a sequence of these. So like the probability distribution you get is extremely high-dimensional. So doing anything exactly is basically impossible. So we have to rely on approximate methods like Monte Carlo.
Some more questions? So it was a nice couple of talks on the same topic. Continuing. See you on next edition of the of the conference. So see how you progress. the sequential Monte Carlo, I think, is promising. So probably there you can even include some you need to see how the large data is structured. Because probably it's so because talk-show larger models, you need to select pieces where which portions of mathematics correspond to which portions. So the cluster is there.
Right.
So maybe there you can see structure of what to be checked first and second, depending on the output of the previous analysis to go to the next one. It looks to be mathematical sense. It's good to combine both the symbolic ones and
Yeah, absolutely.
quantitative ones. So then perhaps we can have small rest and then the hypothesis is that so page is there, right? Maybe we stop recording and